talk about muscle tension, okay? So when we talk about muscle tension, we're talking about the force that when the muscle is being stimulated to contract, how much force? So if we have very little muscle tension, then we're not generating much force. If we have a lot, of force being generated, then we have quite a bit of muscle tension, right? So this picture here is basically showing you an experiment. This reminds me of a story when I was in college. We did a physiology lab in which we did this experiment. Literally, we took a frog, we pithed the frog. I don't know if you know what that means. It basically means you just cut the brain out, but you keep the spinal cord intact and everything else. So we set it up just like this. And we would run an electrode to the frog leg, specifically the gastrocnemius. I think we all know what the gastrocnemius muscle is. On us, it's very similar on the frog. So we'd stimulate the frog leg. The more electrical stimulation that we provided to the frog leg, the stronger the amount of force or tension that gastrocnemius muscle would produce. Then it would get to a point where it wouldn't produce any more. There was a maximal point. So that's what this is kind of showing us here. All right. So what we did is we took a muscle, we're hanging a weight from it to kind of generate a little bit of a stretch. Then we hooked it up with some electrodes, and then the electrodes will stimulate the muscle to contract, much like an action potential that a neuron would produce would stimulate a muscle to contract. So that's what we're seeing here with our muscle tension curve here. Right? You're seeing nothing's going on. Generate the stimulus, the actual muscle contraction. It takes a few moments, and we're going to talk about each of these periods here. Right? There's the latent period, obviously the contraction period, we know what that is, and then the relaxation period, we know what that is. But the latent period is going to be the time where we're stimulating the muscle with our action potential. Right? Remember, we still have to wait for the neurotransmitter to release from the synaptic knob, and then we have to generate an action potential that's going to travel along the plasma membrane there, the sarcolemma, go down into the T tubules, release calcium. So all that takes a few moments, and that's what we're seeing here in the latent period. And then eventually, right, we'll start to get that cross-bridge cycling going on, and we'll start to contract our muscle. Right? So we're going to talk about that. But what this graph is displaying to us is what we refer to as a muscle twitch. Okay? That's a muscle movement. Okay? The actual definition of a muscle twitch is one single brief contraction followed by relaxation, right? From one single action potential or one single stimulus, right? You definitely want to be familiar with what the definition of a twitch is, okay? So it's going to take a minimal amount of a stimulus, our action potential, to break that threshold. Remember, our threshold, right, in skeletal muscle tissue is that negative 65 millivolt, okay? All right, so the first delay period is the latent period. Okay? This is basically where we haven't generated we haven't generated a contraction yet, so there's no change in the length of the muscle, none. Okay? So basically what that is, like I described to you, that latent period is when the action potential starts to stimulate the events that occur at the synaptic knob. And then all of that leading up to when we start to produce our power strokes. All that falls into the latent period. Right? So now when we start to generate our power strokes and our thick filament starts to pull the thin filament by itself, right? Now we're going to start to generate tension. Okay? And that will increase, right, as more of that power stroke occurs. And then of course, right, like we've talked about before, when we stop with the power strokes and stop with the cross-bridge cycling, then our muscle is going to undergo the relaxation period, okay, where we're going to stop releasing neurotransmitter, we're going to stop generating an action potential, and calcium gets pumped out of the sarcoplasmic reticulum back into the sarcoplasmic reticulum. That happens here in our relaxation period. So that's that part of the curve where the tension starts to drop down. Okay? And we'll drop back down to our baseline. But then again, that has to do with the elasticity, and the protein that's responsible for that is that connectin there. Okay? So we start to release our cross bridges, all right? ATP starts to pop the myosin head off of the actin. Calcium goes back into the sarcoplasmic reticulum. Okay? That's going to be this part right here. So here's our relaxation period. All those events that I talked about that occur during relaxation occurs here. So the contraction period is relatively short. Okay, relaxation period is a little bit longer, right? That's a muscle twitch. So keep that in mind. It includes the stimulus. It includes the actual contraction followed by the relaxation. All right? Okay. So question for you. What events are occurring in a muscle that produce different components of the muscle twitch? All right, so the latent period, all those events that we talked about leading up to our power stroke contraction, we start to generate our power strokes, moving the thin filament past the thick, then our relaxation, all those steps that we talked about. Okay, we're releasing the cross bridges, right? We're getting rid of calcium out of the sarcoplasm, moving it back into the sarcoplasmic reticulum. Okay. All right. That leads us up to this next concept of motor unit recruitment. Okay. So what happens now? All right. That muscle twitch explained what happens. Yeah, I can go back. All right. This one here or the previous one? One more. Gotcha. All right. So now we're going to talk about recruitment. So what that means is it's just like Army recruiting. When they go out recruiting, they're going to try to get more and more people. When we talk about motor unit recruitment, we're going to now try to increase the amount of what we call motor units or muscle fibers and their neurons, the motor neurons that innervate them. We're going to try to increase that because remember, the more muscle fibers that you have involved in a contraction, the more powerful the force of the contraction can be, or the more power or the more tension we can actually produce. Okay? So what we're going to see is, all right, how our muscles can actually vary the amount of force that they generate. I mean, do you honestly, the example that's listed up here on the board there is, do you use the same amount of force to pick up a pencil as you would a 50-pound suitcase? No. Okay? And that all involves what we call motor recruitment. Right? So what will happen is, right, the experiment that we were discussing, at a certain voltage, you'll recruit, all right, a certain amount of muscle fibers. Now what happens if we increase the voltage? Okay? So wouldn't you think that if I increase the can't talk tonight. If I increase the voltage, then I could probably get more muscle fibers and therefore get more muscle tension to occur. Okay? And that whole concept of motor unit recruitment, right, I'm going to come right back to this slide, is defined by what a motor unit is. And so for us to really understand, I should have put this slide first before I talked about the motor recruitment, but regardless, a motor unit, right, is this right here. One single motor neuron and all of the fibers that it controls. So you can have one single motor neuron control one muscle fiber, or one single motor neuron could control 1,000 muscle fibers. Okay? There's a ratio involved here. So that's what we're including. Right? So the larger the ratio, so if you have what we call a 1-to-1 ratio, one motor unit and one muscle fiber, you're going to have much more fine control. Right? The eye, for example, the motor units in your eye. Okay? You have more closer to a 1-to-1 ratio. If you have a 1 to 1,000 ratio, right, one motor neuron will innervate 1,000 muscle fibers, that's going to be more like your quadriceps. Okay, you're not going to have as fine a control with that, right? So we're going to spread that stimulation over a wide area there. Okay, so keep that in mind, right? The ratio, the smaller the ratio, the more fine motor control you have. The larger the ratio, all right, the less fine motor control that you're going to have. So that leads us back, now that we know what a motor unit is, okay, if we stimulate more motor units, right, we will definitely increase the degree of force that we're generating here. Okay, so at a very small voltage, we're going to recruit, let's say, 5 units. But if we start to double that, then we can recruit 10 motor units. And then if we double that, we can recruit 20. So the more that we're able to recruit, the larger the amount of tension that we're able to generate. Okay? And that's what this graph here shows. Okay? This graph shows, all right, what happens when we start to increase our voltage. So we're starting off with about 2.2 volts. We get a little bit of muscle tension. Now, all right, we go to 3.4 volts. Bam! Now we're getting more muscle tension because we are recruiting. You can see here, all right, it's highlighting, right? On the minimum amount of voltage, we're recruiting 2 muscle fibers. Okay. Now, when we go up to 3.4, now we got 4 to 5. And then when we increase our voltage even more, all right, we go up to, the red is indicating what ones are being activated. All right, now we're getting up to, I don't know, 8. You can see as we increase our voltage, we're recruiting and getting more muscle fibers involved until we've recruited them all. And then we cannot generate any more muscle tension. Even though we keep turning up the voltage, we recruited everything. There's nothing more that we can do. So we've actually peaked out here, right? So this is showing you what happens when you recruit 1 unit, then 2 unit, and then motor unit 3 is recruited. We start to increase, all right, our muscle tension here, okay? But eventually, we'll have recruited all of them, and we will reach our maximum contractive force there. Okay, you guys got that concept there? Actually, really like that graph there. It makes it a little bit easier to understand. Okay, so going back to the motor unit then, remember, the degree of control, all right, has to do with the size of the motor unit. Okay, so small motor units, all right, they're going to have a finer amount of control. The larger the motor units, all right, several thousand, right, they'll have a smaller degree of control. So again, here we see another inverse relationship. Okay, we saw it with pH in chapter 2, excuse me. Okay, we saw it, where was the other time that we saw inverse relationship? Chapter 9. Remember, stability versus mobility. Okay, that was an inverse relationship. If you have more of one, you get less of another. And so what we're seeing here is the larger the motor unit, okay, the larger the motor unit, the smaller the degree of control. Wait, yeah. And vice versa. The smaller the motor units, the larger the degree of control. Finer movements. Okay. Okay. Muscle tone. Oh my gosh, I use this all the time with people. Right? You ever gone up to somebody? It could be a person, it could be an animal, and I don't know why you'd give an animal a back rub, but if you were giving somebody a back rub, and you're like, oh my gosh, and you're feeling their muscles, especially the trapezius muscles, and you're like, oh my gosh, this is so tight. What is going on? You're very tense, right? What you're doing is you're telling them that their muscle tone is horrible. All right, because what they're doing is if they're sitting there and they're not engaging the muscle, it's in the resting state. Okay, if it feels very tight, very stiff. Now, there's also the fact that that person just might have a decent amount of muscle mass, and that they have their fits, right? But when you are resting and not doing anything, during that time, your motor neurons, all right, will just involuntarily send nerve signals to the muscle fibers, okay? It's like that. I always thought of it as that concept of you don't use it, you lose it kind of thing, okay? Well, this is what happens when you're in a resting position, okay? You're not using, like, especially at night, right? Normally when you enter into REM sleep, that is usually the best time to assess your muscle tone, okay? Because usually the neurological input to your muscles is at a minimum, okay? So even when we're sitting here, all right, like muscle tone in my legs are still pretty decent only because we're getting this involuntary nervous stimulation that is going to that muscle there, right? So basically, your motor units are just randomly being stimulated, okay? And so it allows, like I said, that kind of, you don't use it, you lose it, but it gives you that kind of tone, you know, where people will say, oh, you're tight, or hey, you know, you're really loose, you know, you're relaxed. And it's so that these units, right, don't get fatigued, but they're generating muscle tone, or excuse me, muscle tension. So recruitment is occurring, but it's not enough to actually cause movement, okay? It's enough to where it feels like the muscle is actually quite stiff. Now, when you're in that REM sleep, that REM sleep, right, that's the best time to assess your muscle tone, okay? Because it decreases quite a bit during that time, okay? All right. Oh, yeah. Who here knows about muscle contractions, right? I like muscle contractions because I found a really interesting fact that hamstring injuries in baseball, right, it's a relatively common injury. But the cause of a hamstring injury is not from a concentric muscle contraction, it's from an eccentric muscle contraction. So I'm going to explain it. I'm going to talk about these different types, all right? So there's two major types of muscle contraction. One is isometric, and two, isotonic. Okay? Isometric, easy, right? The muscle length does not change, okay? So the muscle length doesn't change. Perfect example, an isometric muscle contraction is when people go to bodybuilding contests. They're doing the poses, right? And they're holding the pose there, and they're flexing their muscles, but they're holding it. The muscle length is not changing. Another form of isometric muscle contraction is if I was to push on this brick wall, try to move that brick wall. It's not going to move. I'm increasing my muscle tension here, right? But the resistance of that brick wall, all right, I'm not moving the brick wall, all right? And I can keep pushing as hard as I possibly might, all right? And I can increase the tension, but the resistance is not overcome, and that muscle length stays the same. It does not change. All right? So the other type of muscle contraction is isotonic. This is when you generate enough muscle tension, you overcome the resistance, like if you're lifting weights at the gym, right? Or if you're picking up a baby, all right, or getting something out of the cupboard, okay? So what you see here is a length change occurs, okay? Now, notice I didn't say it gets shorter or it gets longer. I said the length of the muscle will change. So if we shorten the muscle during the contraction, that's a concentric muscle contraction. So concentric muscle contractions shorten the muscle. Eccentric, the muscle lengthens, okay? So when you're running down to first base in a baseball game, right, you are alternating eccentric and concentric muscle contractions between your thighs and your hamstrings. So as I'm straightening my leg, all right, my quadriceps, all right, are contracting. That's a concentric muscle contraction. But at the same time, my hamstring muscles, because that's the antagonistic muscle group, is eccentrically contracting. All right, because it wants to. If the only muscle that contracted in my thigh while I was running, you know, was going to be my quadriceps, one, it would look really funny to watch me run. all right, because as I was lengthening or straightening out my leg, that would look normal, but then I'd almost have to just kind of whip my leg back. So I'd kind of look like this, all right? It was really odd, you know, all right? But that's where the eccentric muscle contraction comes into play, okay? It's kind of odd. Sorry about that. I'm glad you folks at home didn't see that. When you attempt to shovel a load of snow that is too heavy, what sort of muscle contraction are you using? Isometric. Right? You stick the shovel. Well, we don't really. Probably a horrible example to use down here because we really don't shovel snow, right? But if really wet snow where I'm from, my father calls it heart attack snow because it's likely to give you a heart attack if you're of a certain age. So when you stick the shovel into the snow, you try to lift it, all right, and the shovel doesn't move. That's an isometric muscle contraction. The tension that you're generating in your muscles is not enough to move the shovel, which is the resistance, okay? So this picture here is showing you, right? This gentleman, as he's holding the baby up to his face here, okay, he's contracting his biceps brachii because he's holding the baby up to his face. No movement is occurring, right? So the muscle's contracting, right, but it's not enough to overcome the resistance of the weight of the baby. So when he starts to bring the baby up towards his face, all right, that's concentric because the biceps brachii muscle is shortening, okay? When he starts to lay the baby or lower the baby back down, maybe put the baby back in the crib, all right, the biceps brachii muscle is lengthening, okay, but it's still contracting, okay? It's just that eccentric, the muscle gets longer during contraction. Concentric, the muscle gets shorter during contraction, all right? One of the things that you do want to take note of during isometric muscle contractions is that you get an increase in blood pressure, okay? You have to be careful, and that's why they always say, and again, we don't have to worry about it too much down here, right? But shoveling snow. It's always, when I was growing up, living up north, they'd always put out alerts for shoveling, and they would always put out a public service message saying, you know, for older patients, be very careful when you're shoveling snow, because one, if you have heart issues, blood pressure issues, right, it can increase your blood pressure. Right? It's called the Valsalva maneuver. It increases your intra-abdominal pressure, right, as you're shoveling snow, right, and that can cause several problems. Think about it. What happens when you're outside and it's cold, right? Thermal regulation. Okay? We learned this back in chapter 1. Your peripheral blood vessels vasoconstrict. So you shunt blood away, all right, from your skin and move it deeper into your body, mainly into your core, right? Well, what happens is, right, all that blood goes into your core and it increases the pressure, all right, on the blood vessels inside your body, okay, that aren't on the periphery. So when you start to engage in an isometric muscle contraction, now you're increasing that pressure even more, and you're going to spike your blood pressure up. All right. Length-tension relationship. This is an important concept that you definitely want to take note of, all right, because different lengths of your muscle, okay, will actually produce, right, more or less tension. Okay, so let me just read this here. The tension of a muscle produces, I can't even think tonight. The tension a muscle produces depends on its length at the time of stimulation. Okay, so if you have a muscle, right, that's completely all the way as short as possible or all the way as long as possible, right, it's going to vary in the amount of tension that it can generate compared to when your muscle's just at rest. Right? So keep in mind, depending on where it is, fibers at the resting length, okay, are going to generate the most force. And the reason why is this right here. An important concept that you want to know, because when you get into IO 211, you're going to talk about contractions of the heart, and it's called Frank-Starling principle. You don't have to write that down. Right? But when you learn about the Frank-Starling principle, that talks about the amount or the force of the muscle tension that your heart can generate depending on how much blood is inside the heart chamber at the time. Okay? And that has to do with the amount of overlap between the thick and thin filaments. I'm going to come right back to this. So this chart here shows you, all right, it's your length over muscle tension here. All right, so you can see, right, the shorter the sarcomere length, right, the more contraction is occurring during the sarcomere length, right, you're not going to be able to generate as much force, right, and the same thing here, right, when it's stretched, because there's virtually no overlap, right, and this is overlapped as much as possible. You can't contract it any shorter. So what we're seeing here with the resting length, we're seeing the maximal amount of thickened filament overlap, and you can see that is where we're going to be able to generate our maximum force, right, up at 100. Okay? If we overstretch the sarcomere, there's virtually no overlap, right, and consequently, on the opposite, if we can contract everything, right, we're not going to be able to go anywhere. So we're not going to be able to generate hardly any force. So keep in mind, right, the maximum amount of contractile force is going to be at the resting length. Okay? So shortened length, right, weaker force, extended length, weaker force, right, because we have very limited movements, right, because both of those thick and thin filaments are close to the Z disc, right, and there's hardly any thick and thin filament overlap when we're in the stretched position. Okay? So which muscle length can a muscle generate the most tension? Right, the resting length. All right, that's because there's optimal overlap of the thick and thin filaments. It's a good concept to know now, all right, because you will learn it again, not again, but you'll discuss it again when you get into the heart. All right, I'm going to do muscle fatigue and then exercise, and then we'll start doing some brain labeling. And I'll finish up. Hold on. Yeah, the aging of, maybe not. All right, hold on. All right, let's do muscle fatigue first, okay? All right, so what is muscle fatigue? All right, it's the reduced ability to produce muscle tension, okay? So as we fatigue, it becomes more difficult for us to produce muscle force, all right? Primarily, this occurs because we're running out of fuel, right? It's just like your car, okay? When you start to run out of fuel with your car, that's going to be a problem. You're not going to be able to drive your car, all right? Well, when you start to run out of fuel for your muscles, you're not going to be able to produce a strong muscle contraction, or the amount of force that you produce will not be very high, okay? Some other things that can cause muscle fatigue, right? You can have an issue here at the neuromuscular junction when we're talking about calcium, right? If you are hypocalcemic, that means you have low blood calcium. Generally, the calcium levels in your body are low, okay? So if we don't have enough calcium, all right, outside of our neurons, right, it's going to be a problem when the action potential opens up the voltage-gated calcium channels. Because not too much calcium will rush into the synaptic knob, and then we won't have a lot of calcium to coat the synaptic vesicles to cause the synaptic vesicles to move to the synaptic cleft to release the acetylcholine. Okay? So we'll have fewer synaptic vesicles that are going to release the acetylcholine into the synaptic cleft. That's a problem. Okay? Another cause, right, has to do with, right, our perfect example. Dehydration, okay? If you have an issue with dehydration, that means your electrolyte balance is out of whack. Sodium and potassium levels are all skewed. When that happens, it's harder for us to actually cause an action potential to occur. And if that action potential has difficulty, right, occurring in the muscle tissue, then it's going to be much more difficult for us to cause the release of calcium at the sarcoplasmic reticulum, okay? So if we have low levels of sodium or low levels of potassium, right, that can cause a problem for us creating our action potential, right? Then finally, cross-bridge cycling is another possibility, because if we have lots of inorganic phosphate lying around, right, what that will do is it slows down, right, the release of that inorganic phosphate and the ADP from the myosin head. Okay? And if it sticks onto the myosin head, then we're going to have a problem because we cannot get the ATP to attach on. Right? And we already talked about less calcium. If we have an insufficient amount of calcium in the body, well, then we won't have enough calcium to bind onto the troponin tropomyosin complex there. All right, muscle fatigue, effects of exercise. Everybody knows what happens to you when you exercise, right? Especially depending on what type of exercise that you do. If you're a person that likes to do a lot of running, okay, that's going to be great, because what will happen is, right, your body responds to that by generating and putting more mitochondria into your muscle tissue. And as you know, the more mitochondria you have available in your muscle tissue, you will have more ATP production. All right? People that go to the gym and like to work out with heavy things like weights and whatnot, we talked about this in chapter 5, different effects of what happens to tissues. We talked about hypertrophy. Hypertrophy is when we increase the size, not increase the number. What do we call, what's the name for an increase in cell number? You guys remember the name? Similar to hypertrophy. Hyperplasia. Okay, hyperplasia is an increase in cell size, in cell number and in cell size. Hypertrophy is an increase in cell size only. And why is that? Because now we've added more contractile proteins in these muscles, so we can actually have more cross bridges occurring. Okay? We'll also increase the amount of glycogen that we can store inside the muscle tissue, and we increase our mitochondria number. Okay? But for the most part, skeletal muscle tissue will undergo hypertrophy. Okay? But in very limited situations and in very limited amounts, it will undergo hyperplasia. Right? Like if you're taking a needle and sticking it into your butt. Steroids. Okay? That can cause hyperplasia. Okay? But you can also do it naturally. Okay? But most likely, skeletal muscle undergoes hypertrophy. So the opposite of not exercising, okay, will cause a decrease in your muscle mass, all right, and that will cause atrophy. So with atrophy, right, if you're a person that is very sedentary, or if you, God forbid, were seriously hurt and were bedridden for quite a long period of time, okay, through that lack of exercise, like that saying I said earlier, if you don't use it, you lose it, okay, you'll start to see a decrease in the size of the muscle cell, okay? And if it's not reversed, it can become permanent, because what will happen is you'll start to get connective tissue. That's what this here says. MM stands for stands for muscle. CT stands for connective tissue. So what will happen is that your muscle tissue will then start to convert into connective tissue. Connective tissue can't contract. Connective tissue doesn't have elastic properties. Okay? So you lose the ability to stretch the muscle, lengthen it like it used to be able to lengthen, like through stretching. You lose its ability to contract. Because like I said, connective tissue doesn't contract. Okay? And so if you decrease your muscle tissue amount, you'll lose definitely power and muscle tone. All right, I'm going to stop here, and yeah, let's stop here. And let's do some labeling. I know your brains are full.